Okay, so that could be our goodness of fit measure. Actually, I guess we wanted a goodness of fit measure that had larger values when the fit was better or explained more. So instead what we decided is we'd define our goodness of fit measure R squared to be equal to 1 minus SSR over SST. Okay? It's an arbitrary decision, but that's what it is. And it turns out that the total sum of squares can be decomposed into two terms, the residual sum of squares and something called the model sum of squares. And so then R squared, it could also be written as just the model sum of squares over the total sum of squares. Okay? Here's the model sum of squares, and here's a picture of it. Okay? It's just the fitted value, the sort of difference between the fitted value and y bar. Oh, that's just something about the decomposition. Okay. Okay, so we've got this thing called R squared, and in a bivariate regression, so in the regressions we've seen so far that just have one explanatory variable, this R squared is actually equal to the sample correlation coefficient for x and y. So we have in fact seen this measure before. Why do we feel like we have to define this new goodness of fit measure for linear regression? Well, it is in fact a more general formulation, and it's defined for linear models with more than one explanatory variable. So when we get to multiple regression, we can have the same, we can define the R squared exactly the same way as we just defined it. Okay? And in addition to using R squared as a basic measure of goodness of fit of our regression, we can also use it as the basis of a test of the hypothesis that our slope is equal to 0. Okay? And when we get to multiple regression, it's going to be a test of the hypothesis that beta 1, that sort of the slopes on all of our explanatory variables are equal to 0. Okay? If we have k explanatory variables. And what is, so what's, what exactly is this test? Well, we create this test statistic, which is just equal to n minus 2 times r squared over 1 minus r squared. And it turns out that this thing, under assumption that the errors are normally distributed, has an F distribution under the null. And it's going to be large. So we're going to reject the null if it's large. Okay? So why does that make sense? So basically the idea is if our r squared is large, that means that the variation in x is explaining a lot of the variation in y. Okay? We have a high measure for our goodness of fit. And so this thing is going to be large. Okay? This quantity is going to be large. And so we want to reject the null that the coefficient on x, this beta 1, is equal to 0. Okay? If the x does a good job of explaining, the variation in x does a good job of explaining the variation we're seeing in y, then beta 1 isn't equal to 0. Okay? Or with high probability, we can reject the hypothesis that beta 1 is equal to 0 in that case. Okay? And so then we want to, when this is large, that's when we want to reject this hypothesis. Okay? Does that make sense? Somewhat? Okay. We'll see the F test again.